Welcome back to the series on statistics. In this video, we're going to talk about Poisson distributions. It's going to be the second type of probability distribution that we look at. This is going to deal with problems that are similar to the one that we were looking at right here. If a business receives on average 2 calls between 12 p.m. and 1 p.m., what is the probability that they receive 3 calls in that same time interval? And so we're dealing with situations where we have discrete numbers of occurrences. In this case, it's the number of calls that the business is receiving. You can't have half a call, you can't have a third of a call. And so it says on average we get 2 calls between 12 p.m. and 1 p.m. And we're asked what's the probability that they receive 3 calls in that same time interval. And so it's taking a known constant mean rate, which we call lambda, which in this case is 2. And it represents the average number of calls in this time interval. And we're trying to figure out what the probability is that they'll get a little bit more than that. They'll get 3 calls instead. Now, it might not be immediately obvious, but we actually already have the tools in our toolbox in order to solve these types of problems. So if I were to draw a number line here, and on here I put this start point of our time interval and this end point here, we know that the average number of calls that we receive over this time interval is going to be equal to 2. And so this is the constant mean rate, or the average number of occurrences over the entire time interval. Now, if we were to make the assumption that the probability of receiving a call at any point in this interval is the same at any other point in this interval, then what that allows us to do is to break this interval up into smaller sub-intervals. So for example, I could draw this, I could draw a couple lines here and say, I'll break this up into 4 equal sub-intervals. So this would go from 12 to 12:15 to 12:30 to 12:45 all the way up to 1. And we can, if we make the assumption that at any point here, there's like no point on this interval where you're more likely to receive a call than at any other point, then what we could do is we could break up these intervals, and we could say that each one of these sub-intervals will have an equal probability of receiving a call, as long as we make that assumption. And so what is that probability? Well, we can actually model this as a binomial distribution, and we could say that each one of these sub-intervals has the probability of receiving a call or not receiving a call. And so there's only 2 possible outcomes in each one of these sub-intervals. I'm going to put a little asterisk by that, which I will return to in a second. But for now, I'll ask you to suspend your disbelief and say that in each one of these sub-intervals, there's the possibility of receiving a call and the possibility of not receiving a call. The possibility of an event occurring or the possibility that the event does not occur. And so if we want to discover what the probability is, well, here we have a binomial distribution with 4 trials. And we would want that the mean of the binomial distribution, which is the number of trials multiplied by the probability of success, or the probability of the outcome occurring in each one of those trials, we would want the mean of this binomial distribution to equal this constant mean rate, which tells us the average number of calls that we're receiving over the interval. If this is actually true, and this is the constant mean rate over the interval, then the mean of the binomial distribution, or the expected outcome of the binomial distribution of these sub-intervals, should be equal to this constant mean rate. And so we could set this equal. And then what we could do is we can solve for the probability of having an event occur in each one of these sub-intervals simply by dividing each side by the number of trials, or the number of sub-intervals. And that gives us a probability of a call happening in each one of these sub-intervals, or a event occurring in each one of these sub-intervals, of lambda here, that constant mean rate, divided by the number of sub-intervals that we draw. And so since we've made the decision here to break this up into 4 sub-intervals, then each one of these sub-intervals will have a probability of receiving a call, the probability of one of these events occurring, receiving a call, of that constant mean rate divided by the number of sub-intervals, or the number of trials of a binomial distribution that we're modeling here, or that we're using to model the situation. The probability in each one of these sub-intervals of receiving a call is just going to equal 2 over 4, which is 0.5. And so the probability that we will receive 3 calls, if we choose to break this up into 4 sub-intervals, is just going to be the probability x is equal to 3 is going to be equal to our binomial PMF here with 4 trials, a probability of success of 50%. That's what we calculated here. And we want to have 3 calls occur. This is just going to be equal to 4 choose 3 multiplied by 0.5 to the power of 3 multiplied by 0.5 to the power of 1. And if you plug that all into a calculator, either the binomial PDF or this formula here, you will get a value of 0.25. And so if you chose to break this up into 4 subintervals, you would estimate a probability of 25% that you would receive 3 calls over the course of this entire time interval. And now, while I'm going to admit that this actually is not that bad of an estimate in this situation in particular, we can definitely do better. And the reason we can do better is if you go back to when I said I was going to place an asterisk, we are implicitly making the assumption that in each one of these subintervals, there are only 2 possible outcomes, that you will either receive a call or you won't receive a call. That's it. But actually, there are more outcomes, because if you take this example, for instance, we're looking at the time interval from 12 p.m. to 1 p.m. And if you were to break this up into 4 different subintervals, we're talking about intervals of 15 minutes of length. And while in this case, when you're receiving an average of 2 calls over the course of an hour, it's not very likely, but it's certainly possible that in each one of these subintervals, there's a chance that you will receive more than 1 call. And so there's not actually only 2 outcomes to each one of these subintervals. But we can minimize the error that we're getting here by failing to take into account those possibilities, by decreasing the length of this interval. And if we decrease the length of this interval enough, for instance, if I decrease this interval down to a length of, instead of 15 minutes, maybe 15 seconds, then the probability of receiving more than 1 call in an interval of 15 seconds in length, that's going to be very, 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 very low, and it might as well be negligible in this case. And so let's see what happens as we increase the number of trials of this binomial distribution or decrease the length of these subintervals. Let's see what happens to the resultant probability that we will estimate by decreasing the lengths of these subintervals. So I've reorganized everything here to kind of make this a little bit easier. So here, let's see what happens when we use 8 subintervals instead of 4. In this case, each one would be a length of 7.5 minutes, 7 minutes 30 seconds instead of 15 minutes. And so visually, we're talking about intervals of this length here, each one with an equal size. The probability of a call occurring in each one of these subintervals is going to be approximately. I am going to use the approximate symbol because now we understand that there is going to be a small chance that you'll receive more than one, or that more than one event will occur in each one of these subintervals, even as we're decreasing this length further and further and further. And so here, the probability is going to be approximately equal to that constant mean rate divided by the number of trials here, which in this case, we're dealing with 8 trials and a constant mean rate of 2. And so that's going to be 2 divided by 8, which is just going to be 0.25. And so this would be a binomial distribution with 8 trials and a probability of receiving a call, or the probability of success, of 0.25. And so the probability here of having 3 calls would be equal to, we would have 8 choose 3 multiplied by 0.25 to the power of 3 multiplied by 0.75 to the power of 5. And if you evaluate this, it looks like you'll get about 0.208. And now let's try to use 16 subintervals. I'll go through this one a little bit faster here. Our probability will be approximately equal to 2 over 16, that constant mean rate, divided by the number of subintervals. Once again, it's approximate because we have to keep in mind that although we are using smaller and smaller subintervals, there still does exist the probability of having more than 1 call within each one of these subintervals, even though it is not likely. And so we have this probability of 0.125. So the probability of receiving 3 calls over the course of this entire interval would be approximated well by the binomial PDF for a series of 16 trials, each with a probability of 0.125. And if the probability of receiving 3 calls using that as an approximation would be 16, choose 3, multiplied by 0.125 to the power of 3, multiplied by 0.875 to the power of 5, which looks to be just about 0.193. 0.193. Now, here you might be noticing something interesting, which is that as we move from 4 subintervals to 8, as we double the amount of subintervals, we're losing about a 5% probability here. So when we use 4 subintervals to estimate the probability of receiving 3 calls over the course of this entire interval, based on the information that we had, we got a probability of 25%. When we increase the number of subintervals, sort of improving our estimation here by reducing the chance of that error that would come as a result of failing to take into account the possibility of receiving more than 1 call in each one of these subintervals, we lost some probability here. It went from 25% to about 21%. But then as we doubled the amount of subintervals again, adding an additional 8 subintervals, we went down from 21% to about 19%. And so even though we doubled it once again, the error only dropped about 2% as opposed to the initial 5 or 4% drop that we saw roughly. And so it does appear that we're converging in on something, and that's going to give us a clue as to the direction that we're going to head with this. But first I want to talk about why this on its own is already a very good estimation. This is a very good approximation for this situation. And I want to talk about exactly the reason why this is a good approximation. And so the way that I'm going to show that this is a good approximation is I'm going to zoom in on one of these subintervals. So if there's 16 subintervals and we're talking about a total interval of an hour, if we divide that up into 16 minutes, we're dealing with about 3 minutes and 45 seconds. So this is just going to be this subinterval from 12 to 12 minutes, 3 minutes and 45 seconds. And I want to treat this as if it is a new original interval. Basically, we're going to do this process on this subinterval itself. So what would be the expected value that we would get for this interval? Or what's the lambda here, this constant mean rate that we would expect from 12 to 12 minutes, or to 12, 3 minutes, and 45 seconds. This constant mean rate is just going to equal the original constant mean rate divided by the number of subintervals, as we saw up here. And so this is going to be 2 divided by 16, which is about 0.125. That's going to be the expected number of calls that we'll receive over the course of this subinterval. And now what I want to do is I want to break this up into an arbitrary number of subintervals, or some smaller amount of intervals. And here I'm going to use 100 subintervals just to give a very good estimation. And then I want to calculate what the probability is that we will receive more than 1 call, because that is going to be the situation in which we are getting some error here. And so what is that going to be? Well, using 100 subintervals here, then the probability of receiving more than 1 call would be 1 minus the cumulative binomial CDF function. That binomial CDF function, the cumulative distribution function for a binomial distribution with 100 subintervals here. So 1 minus the binomial CDF. Here we're doing 100 additional subintervals. And each one of those is going to have a probability associated with it of 0.125 divided by 100. And let's see here, we want to include the possibility of getting 0 calls or the possibility of getting 1 calls, because those are both valid possibilities and they're not going to interfere with our design here. But if we get more than 1 calls, then that is actually going to represent some error here, because we're essentially ignoring that possibility when we're carrying out this approximation here. That's what's causing us to get some error, and it's why the error is decreasing as we increase the number of subintervals. But if we do 1 minus the cumulative distribution function of this binomial distribution that's approximating the number of calls that we'll receive in this subinterval, and we do 1 minus that cumulative distribution function evaluated at 1, both 0 and 1 are valid possibilities for the length of this subinterval, then we'll get the probability of receiving more than one call in the subinterval, which would be the probability of getting some kind of error in each one of these subintervals. If you do this, if you carry out this calculation here, you're going to get a value that's less than 1%. And so in this case, even, that's a very bad, I'm going to draw that better. Less than 1%. And so in this case, even with just using 16 subintervals, we have reduced our possibility of error in each one of these subintervals to less than 1%. And we can calculate it just like this by breaking it up into additional subintervals and seeing what the probability is of receiving more than one call, more than one event occurring in each one of these subintervals. Once again, just to repeat that because I do think it's important, in each one of these estimations, we are implicitly assuming that in each one of these subintervals, the respective subintervals, there is only the possibility that you receive 0 calls or 1 calls. When we make that assumption here with 4 subintervals, the possibility of error is pretty high because there is actually a possibility in each one of those subintervals that is not insignificant that you will receive more than 1 call, which violates the assumption that we're making when we use this binomial distribution to approximate this problem. Now, the estimation does improve as we get down to smaller and smaller subintervals using more and more of them. And at the point when we start to use 16, we have a chance of error in each one of these subintervals of less than 1%. Now, there is 16 subintervals, and so, you kind of have to balance that. But in general, smaller and smaller and smaller subintervals, more and more and more subintervals is going to improve the accuracy of this approximation. And so just to reiterate, this is a very situational statement I'm making when I'm saying that this is a good approximation. There's 2 things here. Number 1, our constant mean rate is very low. We're only getting an average of 2 calls over the course of this entire hour-long interval, and so breaking it up into 16 subintervals, the probability of receiving a call in each one of those subintervals is roughly 12.5%. And so when we have such a small probability with even only 16 subintervals, as I've shown mathematically here, the possibility of getting a erroneous outcome, wherein in any given one of these subintervals, we have more than 1 call, which would throw off the accuracy of using this as an approximation for our problem here. The probability of that error occurring is less than 1% in this situation. You can imagine situations where this isn't true. There's another reason why this might be a good approximation if you were doing this in real life. Here we're dealing with an actual number of calls, and each one of these calls is going to take up some amount of time. And so as we're breaking this up into 16 subintervals, we go down from an entire hour to just 3 minutes and 45 seconds. And depending on what these calls are regarding, you can imagine that there are calls that could be lasting on average longer than 3 minutes and 45 seconds. So the probability of having more than 1 call in each one of these subintervals could be very, very slim, almost negligible. That could be the case. Once again, this is situational. But as it is situational, you could imagine there are situations in which this wouldn't be a good enough approximation. For instance, if there was a highly unstable radioactive isotope that was decaying at a specific rate, but we wanted to know what the probability of having a different number of or a different number of decays in that same time interval was, or the probability of some number of decays in some different time interval was, then we wouldn't maybe have a good enough approximation using just 16 subintervals, because unlike a phone call, which actually does take some time to complete, a radioactive decay happens nearly instantaneously in a matter of nanoseconds, or even less than that. And so in those situations, we might want to use many, many, many more subintervals. And the point is that if we want to minimize this error, as you can see, the error here is very small. Just by using 16 subintervals, we have an error of 1%. We can make this error effectively 0 by taking the limit as the number of subintervals here goes to infinity. And so that's going to be the next part of this, and that's how we're going to actually derive the Poisson distribution. We're going to break this interval up into an infinite amount of subintervals, each with an associated probability of lambda over the number of subintervals. we're going to take the limit of this as n goes to infinity, or the number of subintervals goes to infinity, and in doing so, we're going to make this error asymptotically is going to approach 0, and we're going to get the exact probability of this many calls occurring in that time frame, or whatever number of events are occurring in that time frame. And so summarizing our objective here, our goal is to take this situation where we have a constant mean rate, a known number of events that occurs on average in a given time interval, and we want to figure out a way to calculate the probability of different numbers of events occurring in that same time interval based on that information. The way that we're going to go about doing that is we're going to take that time interval and we're going to break it up into subintervals. And with each one of those subintervals, we're going to associate a probability of having the event occur in each one of those subintervals. And then we're going to use the number of subintervals. We're going to take that as the number of trials for a binomial distribution, and we're going to use that to model the situation in order to calculate the probability of receiving a different number of events, a probability of a different number of events occurring. But we're going to keep in mind that by breaking this up into discrete numbers of subintervals, there is always going to be some error that is going to come by using a binomial distribution in order to approximate this situation. And the error is going to come as a possibility of, by using the binomial distribution, we are implicitly assuming that in each one of those subintervals, there is only the probability that the event either occurs or it does not. But of course, there is the probability, even if it is slim, that there could be more than one event occurring in each one of these subintervals. And if we want to minimize the error and get rid of that possibility, what we have to do is take the limit as the number of these subintervals goes to infinity. And if we break this up into an infinite amount of infinitesimal subintervals, and then we can neglect the possibility of more than one event occurring in each one of those subintervals, and we can get a precise answer to this question that we're after, or the probability of different discrete amounts of events occurring in this interval based only on a constant mean rate, or a known average number of events that occurs in an interval. And let's carry out this process in general terms here. So the probability of the number of occurrences in this interval equaling some constant, we'll just call it k, is just going to be equal to the limit as the number of subintervals, or the number of trials in this characteristically modeling binomial distribution, goes to infinity. And then we're just dealing with the binomial PMF, or the probability of the event occurring in each one of these subintervals. And so that's just going to be n choose k here, multiplied by that probability, and we know what the probability is. That's just that constant mean rate divided by the number of subintervals. And so that's going to be to the power of k, multiplied by 1 minus, or the complement of that probability of the event occurring, to the power of n minus k. And so let's try to deal with this and see if we can find an expression for the probability of different numbers of events occurring based only on this constant mean rate. And so I'm going to make a couple simplifications here, or they might not seem like simplifications at first, but things kind of need to get a little bit worse before they can get better. So here we're going to have n factorial over k factorial times n minus k factorial. That's just going to be the definition of this n choose k here. This is going to be lambda to the power of k divided by n to the power of k, just distributing that exponent. And then here, I'll write out these multiplication symbols. Here I'm going to do 1 minus lambda over n to the power of n divided by 1 minus lambda over n to the power of k. And so now everything just needs to be rearranged a little bit. And so I'm going to keep the n factorial where it is, as well as the n minus k factorial, but I'm going to move this k factorial as it does not depend on n at all. And I'm also going to move the lambda to the power of k, because once again, it doesn't depend on n. And I'm going to take this expression and move it into this term, because they're both being raised to the power of k. So this is just equal to n times 1 minus lambda over n to the power of k. So making all of those simplifications, I'm going to have n factorial over n minus k factorial. And then here, I'm going to have 1 over n times 1 minus lambda over n to the power of k. And that's just going to be n minus lambda to the power of k. And then finally, over here, I'm going to move both this lambda to the power of k and this k factorial. And so I'm going to have 1 minus lambda over n to the power of n times lambda over k factorial. And now the limit of the products of all these terms is going to also be equal to the product of the limits. And so what I'm going to do is I'm going to rewrite this as the limit as n approaches infinity of 1 minus lambda over n to the power of n divided by lambda to the power of k divided by k factorial multiplied by the limit as n approaches infinity of, here we have n factorial over n minus k factorial, n factorial over n minus k factorial, parentheses there, multiplied by 1 over n minus lambda to the power of k. And so this expression here, the only term involving the n is this one right here. And if you don't recognize this, you should watch my video on e to the power of x, but you should recognize that the limit as n approaches infinity of 1 minus lambda over n to the power of n is just equal to e to the power of negative lambda multiplied by lambda to the power of k, all of that over k factorial. Now, we still have to deal with this limit here. And so what I want to point out is that this n factorial over n minus k factorial, this is just n times n minus 1 times n minus 2 times n minus k, and then we're dividing by n minus k factorial. So then this is going to also keep going down to times 2 times 1, but we're dividing by n minus k times n minus k minus 1 times 2 times 1. And so all of these terms are going to go away and cancel. But the point is that when we're getting rid of n minus k terms, we're taking n terms and we're canceling out n minus k terms. What are we going to be left with? Well, we'll be left with k terms. We had n terms, we got rid of n minus k terms, so we will have k terms remaining. And so this is going to be just a series, or a product, I guess, of k terms that look like this. It's going to be n times n minus 1 times n minus 2 times all the way down to n minus k plus 1. And so here we're going to have k terms. And why is it special that we have k terms? Well, if you look here, this expression here, n minus lambda, which is just some constant to the power of k, that's also going to have k terms. This is just n minus lambda times n minus lambda times n minus lambda k times. And so if you take this one here, this also has k terms, and we can match them up one to one with each one of these terms. So this is just lambda times, or n minus lambda times n minus lambda. It's a very bad lambda, but it's fine. Times n minus lambda. Try to redeem myself there. Times n minus lambda, etc. Or actually, that would be the last term if this is the last term there. And so what is the limit of this as n goes to infinity? As n goes to infinity, each one of these constants just becomes negligible. And so this winds up becoming the limit of n over n times n over n times n over n times n over n. And the whole thing just cancels to 1, or just winds up being equal to 1. And so the limit of this whole expression here is just equal to 1. And here we're multiplying that limit by this expression here. So if I just clean this up a little bit, what we have is that this whole thing is just going to be equal to this multiplied by 1, which is just equal to the expression itself. This whole limit cancels to 1. And so what we have identified here is this is the probability mass function for a Poisson distribution. Poisson distribution. And so we can actually use this to solve the problem that we were dealing with in the beginning. So let's do that and let's see what answer we get. And so if we remind ourselves of the problem that we were dealing with here, if a business receives on average 2 calls, that's our lambda, between 12 and 1, what is the probability that they receive 3 calls in that same time interval? And so the probability here of having 3 calls is just going to be equal to, using our Poisson PMF, it's going to be e to the power of negative 2 multiplied by 2 to the power of 3 divided by 3 factorial. And if you plug this into a calculator, you'll get a probability of 0.1804. And so if we remind ourselves here of what we originally approximated using 16 subintervals, you could calculate the error that results, the error from only using 16 subintervals. In this situation, if you calculate the percent error here, is approximately 7%. And so 7% error isn't amazing, but it's also not that bad. For all of you who have done experiments in chemistry or something like that, and you calculated the percent error, 7%, it's not something to laugh at. It's okay. And so that's just a point to be made here, is that we got pretty far by just using 16 subintervals in this situation. It wasn't a horrible approximation. But we went through and we derived the PMF for a Poisson distribution in order to get a much, much, much better approximation that ceases to be approximation, is actually the precise answer for the probability of this many occurrences based on the information that we were given, which was just that constant mean rate over the course of that interval. So to conclude this video, I just want to talk a little bit about the differences between binomial and Poisson distributions. The Poisson distribution is used as a specific application of the binomial distribution over a continuous time interval. It's used to model situations where the average number of event occurrences over a specific time interval is known, and the probability of other possibilities is what we're trying to compute. So as an example of that, I have here, if an average of 5 cars drive past my house from 3 p.m. to 4 p.m. on Friday, what is the probability of 2 cars driving past in the same time interval? This Poisson distribution is reliant on a few assumptions. First, we need to assume that the events are independent, but that they don't influence each other. Otherwise, that would throw off the results of this. As you can see, we are using a binomial distribution. It's the number of subintervals approaches infinity, and if the probabilities of each one of those subintervals differed from one another, then we wouldn't be able to use our equations that we derive for binomial distributions in order to approximate these situations. So we have to make that assumption that these events are independent and that they cannot occur simultaneously. And we help mitigate the possibility of simultaneous events occurring by taking the limit as the number of subintervals approaches infinity, as we saw in the derivation. Also, we need to assume that the probability of an event occurring is evenly distributed across the time interval. So just as an example, if we were using 4 subintervals, we need to assume that the probability of an event occurring in the first subinterval is the same as the probability of event occurring in the third subinterval. And so that's why in a lot of these situations, the wording in these problems is pretty important. Here we're talking about if on average 5 cars drive past my house from 3 p.m. to 4 p.m. on Friday, we can reasonably assume that the probability of a car driving past my house from 3 p.m. to 4 p.m. is going to be pretty much evenly distributed across the time interval. If we were dealing with 12 p.m. to 8 p.m., for example, then that probably would not be evenly distributed. 12 p.m., everybody's at work, or at school or whatever. Then at 5 p.m., everybody starts to come home. And so if you look at the subintervals that you would draw around 5 p.m., 6 p.m., 7 p.m., there would be a lot more cars driving by versus from 12 p.m., 1 p.m., when most people are out and about. And so you have to be careful in these situations. You have to think, are we making fair assumptions here, or are they severely distorting the data? Now, binomial distributions, on the other hand, which are the precursor to Poisson distributions. We saw in this video how the Poisson distribution comes from the binomial distribution. It's just the limit as the number of trials in a continuous time interval goes to infinity. We use that to approximate those situations. This binomial distributions are used to model situations in which there are a series of trials, each with only 2 possible outcomes. So just an example, what's the probability of eating 6 heads out of 11 coin flips? These binomial distributions, as we saw in my other video on the theory behind a binomial distribution, if you haven't seen it, I recommend you check it out. Some assumptions need to be made for the mathematics to actually work out and for us to use these formulas to model these situations, and those assumptions have to be that the trials are independent of one another, so the outcome of one trial doesn't influence the outcome of another. If it did, we wouldn't be able to use the formulas, as I demonstrated in my video on the theory on that topic. Each trial can only have 2 possible outcomes, the possibility that it happens or it doesn't, for instance, in the example of the Poisson distribution when we're using these binomial trials to model these situations. And also we need to assume that the probabilities of either outcome are constant across trials. So once again, you could kind of see some similarities between the assumptions in both of these distributions. But both of these distributions are discrete probability distributions. You can't have, for example, here, half a car driving by your house. You can only have discrete whole number amounts of cars that can drive past your house from 3 p.m. to 4 p.m. on Friday. And so both of these distributions model discrete outcomes and the probabilities associated with them. All right, so I hope that you guys enjoyed that video. I hope it was entertaining. If it wasn't, I hope you learned something or there's something you could take away from it. Thank you guys for watching. In the next video, we're going to start talking about continuous distributions. So this is going to be my last video on discrete probability distributions. Then after this, we're going to start moving into the continuous field, and we're going to use a little bit more than just limits from calculus. So I hope you guys are looking forward to that. I'll see you guys in the next video.